Up on the mountains of La Palma Island are placed two telescopes that look at the night sky in search of hints from highly energetic sources.
So behind me you can see the so-called Magic 2 telescope. It has a 17-meter diameter and 17-meter focus, and this telescope is used for doing so-called ground-based gamma ray astronomy for the very high energy range. And in that direction, on 85-meter distance, we have Magic First telescope, which we built 2003, put into operation 2004. And since 2009, these two telescopes are working in coincidence. They work together.
MAGIC stands for Major Atmospheric Gamma Ray Imaging Cherenkov. Gamma ray imaging telescopes are among the latest technological features which astronomers are developing in order to deepen our knowledge about how the universe works.
To judge about the very energetic process, you need to measure the messengers of these very high energies. And the gamma rays are these messengers. They are the same optical photons, but just energy is 100 billion times or 1,000 billion times higher.
The way they work is a gamma ray, when it enters the atmosphere, it can generate a pair of electron and positron. These two particles can generate more particles, 4 particles, then 8 particles, and there's a whole multiplication process. You generate a whole shower of particles.
This cascade of particles moves very fast, faster than the speed of light in air, generating a blue flash of Cherenkov light, similar to the sonic boom created by an aircraft exceeding the speed of sound. But those flashes are so dim that we cannot see them with our own eyes. We need much bigger eyes. And that's exactly what MAGIC telescopes are, large collectors able to catch visible and ultraviolet light.
These images look like a movie rather than a picture because they are very dynamic. Among the Cherenkov telescopes, MAGIC is the one looking farthest in the universe. So we look at the universe at distances close to the Big Bang. And we discover that there are phenomena occurring in the vicinity of supermassive black holes at the edge of the universe. These phenomena can be wild and extremely variable. A black hole of million solar masses, billion solar masses even, can double its power in less than a minute, and this light travels through the universe for a billion of light years before reaching MAGIC.
Since photons have no electrical charge, their journey through the universe is not affected by magnetic fields. Therefore, their identification addresses us to the exact position of the sources that produce them.
And this is the main goal of this science, to understand how it is possible that nature can accelerate particles to enormously high energies.
Detecting high-energy photons from cosmic sources allows scientists to perform further observations in other wavelengths that are crucial in order to assess the nature of the source.
In this way, in the end, we are able to reconstruct the history of the universe, how it was developing.
When a massive star dies, her life finishes in a spectacular explosion, the so-called supernova. Inside the nebula released by the explosion, there's a small dense remnant, a pulsar, a rapidly rotating neutron star, often emitting highly energetic radiation. Pulsars in our own galaxy, the Milky Way, represent the closest targets for MAGIC. One of the most famous pulsars, already known and well studied by astronomers in the last decades, is the one that can be found at the center of the Crab Nebula, the Crab Pulsar. Its mass is about 1.5 times the mass of the Sun, concentrated in an object of about 10-kilometer diameter. It rotates 33 times per second, and it is surrounded by a region of intense magnetic field, 10,000 billion times stronger than the solar one. Since 2008, MAGIC has seen for the first time pulsed emission from the Crab pulsar in the very high energy range, revolutionizing the existing models of pulsars. The twin telescopes recorded from the Crab pulsar the most energetic light radiation that has ever been measured from a star, And the researchers are not yet able to explain how the charged particles are accelerated to these extremely high energies. When we observe with magic outside our galaxy, we find some galaxies which are called active, as they produce in their central parts much more light that cannot be explained by the stellar and dust emission. Active galaxies host at their center a supermassive black hole with masses of million up to few billion times the mass of the Sun. Such active galactic nuclei produce so-called jets, in which the gas is blown into space with approximately the speed of light, as if being ejected from a nozzle. If matter falls onto these objects, this occasionally leads to unusually powerful radiation outbursts. One of these extreme black holes, containing over 300 million solar masses, can be found at the center of IC 310, a galaxy belonging to the Perseus cluster. In 2009 and 2012, MAGIC's high sensitivity enabled the discovery and the study of very high energy emissions from IC 310, providing for the first time indications as to how jets form in the very vicinity of black holes. The rapidly rotating supermassive black hole hosted by this galaxy is surrounded by a magnetic field. In the polar regions, there seem to be strong electric fields which accelerate the particles near the speed of light, thus generating high energies and ultimately gamma rays with very fast time variations. A process similar to lightning in a thunderstorm, which discharges the energy it has accumulated in a region the size of our solar system. In 2015, MAGIC obtained the very first high-energy emission from two of the oldest active galaxies known, QSO B0218 plus 357 and PKS 1441 plus 25. The emission detected from these galaxies has been traveling for half of the age of the universe. The discovery is extremely exciting because this kind of emission was totally unexpected. Such emissions are supposed to be attenuated on their way to Earth from what is called the extragalactic background light, generated by stars and dust. When a gamma ray encounters starlight, it transforms into an electron and a positron and is lost to astronomers. The farther away the active galaxy is, the less likely its highest energy gamma rays will survive to be detected. Thanks to MAGIC observations, the current models of the extragalactic background light, constraining the evolution of the universe from its middle age until today, were tested for the first time up to energies never reached before. Dark matter is the major component of universe. There is 4 times more dark matter than normal matter, but its nature is still unknown. Dark matter does not emit or absorb directly light. Its presence can be inferred only by its gravitational effects on stars and galaxies. The most popular theory proposed to explain the nature of dark matter, the so-called supersymmetric scenario, foresees that when 2 dark matter particles collide, they may annihilate and produce different particles, including gamma rays with some small probability. MAGIC has observed targets that are considered among the best candidates for dark matter searches in the sky, some satellite galaxies of the Milky Way. Despite no signal was found by MAGIC from those targets, this study showed how null detections can be used to discard some of the models proposed by scientists to understand dark matter's nature. In the last 10 years, MAGIC has largely contributed to open a new window on the universe by discovering several new active sources and by initiating the so-called very high-energy astronomy. To go further in the near future, an entire bouquet of similar mirrors will flourish around MAGIC. They will compose a Cherenkov telescope array designed to be 10 times more sensitive and to have unprecedented accuracy in the detection of high-energy gamma rays. But in the meantime, the two magic telescopes will carry on unraveling the secrets about the most violent phenomena in our universe.